Good morning, guys. Give me just a few minutes and we'll get started. Hey, can you go take that somewhere? I'm in class. Thank you. Go take that somewhere. Good morning, everybody. How are you guys doing? Um, you guys unmute yourself for a moment, or tell me how was the exam, or say something in chat about the exam for me. Say
It
hey.
was good.
Okay. All right. Hey. All right. Say hey, everybody. Hey, everybody. Okay. Now y'all can go eat your breakfast. Okay. She's fixing it. Go on and eat your breakfast. Okay. All right. Good. I just wanted to check on that. Just so I am clear about the lab practicums and stuff, because I think it was just some confusion about that. Okay. Hold on just a second. There was an accident. I know that was glass. That was bad.
Loud.
Okay, guys, sorry about that. Kids and glass and everything don't mix well. Um, um, the lab practicums, and I guess some of you guys were confused about the lab practicum or doing a new lab practicum. You could see on Canvas that I took away the lab practicum, the final lab practicum. I think somebody had some confusion about that. Only thing you guys are doing are writing the lab reports for that. Is anybody confused on that part? Because I think some people put down that that was a confusion or something. Can you guys give me some feedback on that so that I can understand what's going on? Because I think some people put particularly on the survey about lab practicums, and y'all had some concern about the lab practicums. I got to put the grades in, but the final lab practicum is not going to be one because we're not in the lab, and y'all just doing the just the lab reports. So I'm just trying to make sure that is everybody clear on that. Did anybody have any questions about that? And can y'all give me some feedback on that real quick?
I think it's pretty self-explanatory if you just read what you sent us.
Oh, okay. That's what I thought. I just wanted to
It's just a lot, but I mean, when you start going through it, it's not that bad. But I
okay,
mean, if we had questions, we could email you.
yeah, yes, that's fine. But I just wanted to make sure because I think some people was unclear on that because I think because I don't know what the other teachers are doing as far as lab practicum, as far as that, because we had a midterm. That's why I try to have two. So if something shall come up that you guys have done one. And usually that's what I do. I try to plan for not this type of thing, but if something came up personally, that at least I've done one and everything like that. So I just wanted to make sure because I think it was just some confusion. And like I said, I don't know what other instructors are planning to do for their lab practicums. Only thing I know is because we can't physically be there to do one, I'm just not going to do one because it doesn't make any sense to try to do one if you can't physically be in the lab. So I just wanted to make sure. So it's no lab practicum, no final lab practicum. There's not a grade for it, even on Canvas. So I just wanted to make that perfectly clear to everybody that you just have to do your lab reports. You do not have to do a final lab practical. And I'm gonna also send an email or announcement out about that just to make sure that we are clear on that. All right. The test scores from the first part look pretty good. We're gonna get started on the last three major chapters of the book that we're going to go over. So we're going to go over chapter 19, chapter 20, and 21. Now, these three chapters really wrap everything up. So I'm going to cut off my video and we're going to get started. Now, chapter 19, going through the slides is a pretty short chapter. But what I'm going to do is go over this today. I know some people have already worked on their, let me see what I say, concept maps. You guys make sure you go ahead and read it and go through it because chapter 19, 20, and 21 really brings everything with chemistry together that you took last semester and this semester and really wrap it up into a bow. So everything, it touches on pretty much everything up to this point, pretty much every chapter. So these last three really bring everything together. Um, Now, we looked at thermodynamics a little bit in chapter 5, and now chapter 19 is getting into really chemical thermodynamics and really bringing all of that together. Now, chapter 5, we talked about the first law of thermodynamics, which basically says energy can't be created nor destroyed. And if we break it down even further when it comes to chemistry, atoms cannot be created nor destroyed. They only change, or the word that I like to use is translate. And then also the energy of the universe is a constant. So energy can be converted from one form to another. That's why I say it translates. Now, we got two things that we're going to look at. Now, we talked about delta H, which is enthalpy, in chapter 5. And enthalpy deals with heat absorbed during a constant pressure process. So we say that delta H, um, under constant pressure is the same thing as Q, which is heat. So we have that. Now, when we talk about entropy, entropy is a measure of randomness in a system, how the molecules really react. So when we talk about this, we have to talk about whether or not a reaction is spontaneous or non-spontaneous. So we get into what we call spontaneity. Now, um, why do we want to get into that? Because we have chemical reactions that just happens, and then we have other ones that need help to make them happen. Now, when we talk about a reaction or a process that's spontaneous, it just goes without any assistance. Now, usually what you have is you have processes that are spontaneous in one direction, they are non-spontaneous in the reverse direction. And one thing that a lot of people confuse spontaneity with is with being fast. There are fast reactions that are spontaneous. There are slow reactions that are spontaneous. They are both out there. Uh, and then when it comes to being non-spontaneous, you can't say that they're not impossible. It just takes more energy for some of them to actually react. Um, so that's what you happen. So what they're showing here is cracking an egg. So pretty much, even if you drop an egg, if you slightly touch an egg, it'll crack. But you can't go backwards and reverse that. You might as well just go ahead and cook the eggs and eat them. So that's what they're showing here. Now, there are experimental factors that really affect spontaneity. Now, temperature, pressure, uh, and let's look at water itself. And how temperature affects spontaneity is ice melting or freezing. So you can see that. So you can have spontaneity other than just dropping the temperature, it'll change. Up in the temperature, it'll change. You don't have to really do anything, it just the atmosphere itself that causes it to change. So experimental factors can cause things to change. Now, when we talked about in chapter 5 about reversible processes and irreversible processes, um, when you have something that reversible, basically the system changes so that the system and the surroundings can go back to its original shape. Now, when you have that, and when we talk about work, work done by the system on the surrounding, that maximizes work done on the system. Now, when you have something that's irreversible, you cannot undo what has happened by exactly reversing the system. Um, Also, keep in mind that any spontaneous process is irreversible. And so that's the thing. That's what we have to look at. And so that's what they showing here. That you got some that are reversible, some that are not. So we have to look at that. And so when you have something that is irreversible, well, reversible, Some factor has to play a part in it becoming reversible. Now, when we dealt with enthalpy, we dealt with delta H. Just so I won't be saying entropy and enthalpy all the time, I'm going to say delta H and delta S. And you guys should know which one I'm talking about. So when we're dealing with entropy, we basically dealing with the randomness of a system. Now, you guys can type into the group chat because I wanted your response on this. Uh, it's the randomness of a system. It's a state function. Now, given the fact that just about a slide or two ago, we were talking about water. Water is in different phases, right? You have a solid, you have a liquid, you have a gas when it comes to water. So water being in its ice form, water being in its liquid form, and water being in steam or vapor form. So when you have that and you think about delta S, which phase would delta S be the highest in? Tell me what you think about that. And I'm gonna keep going because I want you to really think about it. What phase would delta S be the most in? What phase delta S will be the least in? And that will help you out a lot. Okay, so dealing with delta S is a state function, meaning that delta S is equal to S final minus S initial. It can be found by heat transfer from surroundings at a given temperature. And so delta S is equal to Q reversible over T, and the temperature has to be constant. So when it comes to delta H, pressure has to be constant. When it comes to delta S, temperature has to be constant. So I want you to think about that, look at that. Now, when we talk about that, we get into what we call the second law of thermodynamics. Because you're going to see the second law and the third law of thermodynamics. Second law of thermodynamics really states that the entropy of the universe increases in any spontaneous process. So this is what you see here. So if you got something that is reversible, delta S of the universe is equal to delta S of the system plus delta S of the surroundings, which is equal to 0. That is always the case in a reversible process. When it's irreversible, you got delta S of the system plus delta S of the surroundings is always greater than 0. So it either has to be equal to 0 or greater than 0. There's no in between. It has to be that. Now, what about it on a molecular scale? Okay, what happened when you got this? Now, they look at it from Boltzmann, and we're going to talk about Boltzmann constant and all of that a little bit later. Now, they're talking about here gas molecules. Two molecules start on one side of this particular flask, and then what is the likelihood they end up there? And they said 1/2 squared. If you use 1 mole, is 1/2 to the 6.02 times 10 to the 23rd. And they said 0. Gases, when they're in a room, they're in a canister, they spontaneously expand to fill the volume given. And so what happens here on with this when it comes to gases, if you open that stopcock, what's going to happen is the gas is going to diffuse through, go through, and make sure that it make sure that the system is equal. And that's what's going to happen. So gas is going to flow from one area to another area to make sure the whole system is at equilibrium. That's what it's going to do. But you're going to have gas over here at 1 atm, gas over here at 0 atm. What's going to happen is once you open it, half of that gas is going to go over there until it equals the system out. Now, when you talk about thermodynamics really look at the whole system in particular. So basically, thermodynamics give you the big picture, but what happens on the molecular scale? What happens when, for example, you're trying to find a drug for COVID-19? But that's what everybody is dealing with right now. What happened? Because you got to deal with the thermodynamics of that. Because think about it. If you think about it, even something as this with a disease, people have fever, meaning that they have an elevated temperature. How do you fight all of that? So when we look at that, we have to look at statistics. And I know some people are taking statistics online. So you have to look at thermodynamics from a statistical point of view. Uh, however that you look at it, we look at it from the standpoint of what we call a microstate. And a microstate is a single possible arrangement of position and kinetic energy of molecules. So when we're looking at microstates, we are actually looking at the thermodynamics of the system. What is happening on that scale? What can we do to address that? So what do we do? How do we look at that with the micro state? Um, I asked you guys that, and then Boseman use microstates. But before we get into that, again, let's talk about randomness of a system, talk about delta S. Now, when we talk about delta S and we talk about the states, when you talk about ice, and let's see, can I share? Share. And I'm going to come back to that. And I'm gonna come back to, and I got the whiteboard pulled up. So we got delta S, and I'm just gonna put delta S. Now delta S is actually equal to, and we say the randomness of a system, and we say, and that's the change in randomness. I put it like that. In this of a system. That's what we want to look at. Delta X. It's a change in randomness of a system. Now, when we talk about the three things, we're talking about ice, we're going to talk about liquid, and then we're going to talk about steam. Or I just put vapor. All right. So when it comes to those three, what you'll see is ice has a low to no delta S or S entropy. And that's because the molecules are not moving. Okay, when it comes to liquid, it does increase in S. Then we got molecules in motion. Okay, so then when it comes to vapor, I'm gonna put highest of the entropy. And that's because the molecules are moving fast and they are random. I just put randomly placed. So that's what I wanted you guys to see. When it comes to delta S and when it comes to S, you're looking at when you're dealing with the phases, because there's no movement in ice. The molecules are restricted. So because those molecules are restricted, they're in a certain place, you will not have movement with those. When it comes to liquids, it will be more movement when it comes to them. And then the highest one you'll see was in the gas phase or the vapor phase, because they're moving very fast, they're random, they act like they're on their own. So I want you guys to keep that in mind when you talk about delta S and when we talk about that. Now let's get back to our PowerPoint. And so when we talk about this, and we're talking about the movement, how does that relate to these microstates? Because there are so many possibilities. So think about it. Look at different temperatures. So let's just say when you got ice that is melting, so you have two phases there. There can be different microstates at different temperatures. So we let capital W represent the number of microstates. And then entropy is a measure of how many microstates are associated with a particular microscopic state. That's what they're saying. And so the connection between the number of microstates and entropy of the system is this equation. S equal to small k, the natural log of W. So that is what we see here. Now, entropy is a state function. You can have the final minus the initial value would give you the overall change. You will see that. And in this case, you got an increased number of microstates, you can result in a positive entropy change. And when you get that increase in delta S, that means there's more disorder to the system, because the molecules are out of order. The molecules are not in a straight line, they're everywhere. More disorder, more entropy, more S. That's what you see. And so when you do this at a look at it from a state function point of view, you get how should I put it? K natural log of W final minus K natural log of W initial, and this is what you get. K natural log of W final over W initial. So with that, what you need to do is make sure you remember all of these formulas for the next few chapters. I will tell you guys, make a formula sheet. That's going to be very important. That's what I would do. Start making some formula sheets so that you can have that with you, especially for this chapter, because it's going to be a lot of formulas for the next few chapters that you're going to need to know. Now, what happens if we increase the volume of the system? So increased volume means you got increased molecules, and with increased molecules, you're going to have basically increased microstates. So more opportunity for your molecules to be more random. So if you increase temperature, what you also going to increase is the kinetic energy. So when you increase the kinetic energy, there are more places for those molecules to be. So more microstates. So increasing kinetic energy increases those microstates, increasing delta S. That is what's going on. That's the name of the game. So the more microstates you have, the more entropy you have. The more kinetic energy you have, the more delta S you will have, entropy you will have. The more volume or the more materials that you have, the more delta S you will have. That's what you got to think of. If you have more of it, it's more possibilities. that is what I want you guys to get. Now, okay, when it comes to, and I've been saying these molecules, and what do these molecules do? These molecules have motion. They have different types of motion. They can be translational, meaning that they move from one place to another. They can be vibrational, where the periodic motion of the atoms happen within the molecules, so the molecules vibrate. And then you can also have rotation, where these molecules rotate. Now, more atoms, more volume means more molecular motions, meaning more delta S. That is what they just all saying here. So you got increase in motion, you're gonna have increase in delta S. So that's what you have to look at. Now, do these atoms rotate? Do they vibrate? Do they do all three? Yes, they do. They do all of that, especially when it comes to breaking bonds and then redoing those bonds in another fashion or in another state. So it does happen. Now, the number of microstates, therefore the entropy increases with temperature, volume, and the number of independently moving molecules. So the molecules have to move on their own. That's why I say you do have increased entropy when it comes to a liquid, but the molecules kind of move together because they're close together. When it comes to gases, they moving on their own. Each molecule acts as its own entity. And so that's what that is. And I want you guys to really understand this, because when you understand this, some of the questions that you may get on your final exam, some of the questions you may get on an MCAT, they're going to ask you things like this. So it'll be more so not just trying to figure out a math problem, but more so, do you understand the concept behind this? And that's what they want you to understand. Now, remember I just showed you that the entropy increases with freedom of motion. That's what I was showing you earlier. Basically telling you, so S for gas is greater than S for liquid, is greater than S for solid. Okay, so entropy of the system, it really increases. So if you see down here in the left hand corner, that's a crystalline structure, and basically saying the motions are restricted to just vibrations only. That's it. That's the only thing that they can do. They can just only vibrate. They can't translate. They can't move translational. Now, so you got the smallest number of microstates when it comes to ice. Now, when you go to liquid water, you got increased motion when it comes to translation. So the molecules are free to vibrate and rotate, and then you get a larger number of microstates in this case. Then when it comes to water vapor, however, the molecules just spread out. They're independent of one another, and they got complete freedom for translation. So complete freedom. Whereas in liquid, they can translate, but not that much because they are so close together. But they got complete freedom. And then in the gas form, they have the largest number of microstates. So that's what I want you guys to look at. So entropy and physical states, they are related. And that's how they are related. And this brings us to the third law of thermodynamics. And the entropy of a pure crystalline substance at absolute zero is zero. So delta S of anything that is pure crystalline at absolute zero is zero. That's it. It can't go no lower than that. Consider all atoms or molecules that is in a perfect lattice is at 0K. There can only be one microstate. And so if you do that in WB1, natural log of that is going to be 0. Just as simple as that. So mathematically, you can prove that that will be 0 based on this equation. So why do we care about this? Now, there are some things like liquid nitrogen and all of that that get close to absolute zero, but not quite. But we got to look at that possibility, and we got to know that that exists. Now, over here, and in the back of your book, in chapter number 5, we looked at delta H's in appendix C in the back of your book. When you take this next test over these chapters, that is going to be really your friend because delta S is also on those charts. So make sure that if you don't have a book, Google Appendix C. I'll try to see if I have a copy of it so that I can put it on Canvas for you guys. That Appendix C in the back of your book is going to be needed for the next test. So I just want you to have that and keep that in mind. And I'll make sure I make a note of that. Now, over here, this is just a standard table for different ones, but is more of them on that table in the back of your book. So where the delta H's was, the S's was for these different ones. Molar enthalpy for gases are generally greater than liquids and solids, of course. Standard entropies increase with molar per mass, yes, because you got more concentration. Standard entropies increase with the number of atoms in the formula, yes, because you got more microstates. So keep that in mind. Increased concentration, increased volume, more microstates, more entropy. Now, the same way delta H was calculated, delta S can be calculated the same way. And so you can do that with this particular formula. Delta S is equal to the sum of N delta X of the products minus M delta S of the reactants. N and M are the coefficients in a balanced chemical equation. So you same way you did delta H, enthalpy, you can do the same thing with entropy. So that is there. So make sure that you keep that in mind because delta H and delta S are related, and we're going to show you that. Now, heat flows into our system, so and changes the surroundings. Now, how do this affect? How does this affect delta H? How does this affect delta S? Dr. Jones, what are you talking about? So take a look at this. So if you have an isothermal process, you got Q of your surroundings over T equal to delta S of your surroundings. That also equal to the negative negative heat of delta Q, well, not delta Q, but Q of the system over T. Now, at constant pressure, remember I told you Q of system is simply delta H because heat is equal to enthalpy under constant pressure. So you have that, and you have delta S of your surroundings is equal to negative delta H of your system over T. And that's at constant pressure. All right, with that being said, and I want you guys to pay attention to all of this. The universe is composed of a system and their surroundings. So when you have spontaneous process, the universe, delta S, got to be greater than zero. So you got to have that. It has to be greater than zero. So when you have that and it's greater than zero, all right, this is where it all comes together in this little equation that we call Gibbs free energy. Now, for those of you, because I know quite a few of you guys are going to be taking organic chemistry and you got to take biochemistry, you need to put this in your pocket and you need to make sure you remember Gibbs free energy, because after this, you're going to see this in every chemistry class. You're going to see it in a pharmacology class. You're going to see this everywhere. You're going to see it in some of your biology classes. You're going to see this. So just might as well go ahead and record it in your memory, because this is important. The test that my biochem students are taking today is dealing with Gibbs free energy. So you do not run away from it. Do not forget it. You have to keep this. Okay, why do we care? So when it comes to the universe, you got the system and your surroundings. And what you just saw on the previous slide, let me go back to that. Well, this one, you got delta S as your surroundings is equal to negative delta H over T. Now click back over here. Now, when you have that, you have negative delta S of the universe is equal to the system minus delta H over T. Now, if you multiply by negative T, we're just trying to get T out of the bottom. You got T delta S is equal to negative T delta S of the system plus delta H. Now, when you rearrange it, you got negative T delta S of the universe is equal to delta H of the system minus T delta S. And this is called the Gibbs free energy. This is what this is called, Gibbs free energy. Why do we care about Gibbs free energy? You're going to use that a lot. So why do we care? If delta G is negative, the forward reaction is spontaneous. If delta Z is zero, the system is at equilibrium. So there are a lot of different things that can give you what makes a system at equilibrium. This is just another way. Delta G is positive, the reaction is non-spontaneous, but it's spontaneous when it's reversed. So that's what you have to look forward to. So knowing what delta G is when it's negative, when it's at zero, and when it is positive. So you need to know that. But those are going to be 3 questions that's going to be on your next test. So you got to know those. Now, the same thing when it comes to delta S, delta H, because delta H and delta S makes up the Gibbs free energy. You're going to see the standard formation of that. It's going to go the same way. And so N and M in this case is the coefficients in a balanced chemical equation. So you're going to see that. So here, just convention using this, establishing that solid, liquid, gas is at 1 atm of pressure, solution 1 molar concentration, and then an element, delta G, the standard Gibbs free energy of formation is 0. So your diatomic elements, have no fear of ice cold beer. Those diatomic elements, when it's in that state, elemental form, the delta G of formation is 0. Just like delta S will be 0, not necessarily, but delta H will be 0. In those cases, because delta H and delta S make up that, it will be 0. So I want you to keep that in mind. Now, this is a chart right here that I want you to know, because you would need to know this for your next test. How does the size of delta H and delta S affect the reaction spontaneity? You need to know this chart. I'm going to ask you to fill this chart in on your next exam. Please make note of that. I will have you fill it in. Since the reactions are spontaneous, if G is less than 0, the sign of enthalpy and entropy and the magnitude of the temperature matters to spontaneity. So you got to know the signs. You got to know the signs of how it respect that. Questions that I'm going to ask is basically reaction characteristics. What is the sign of these? And you got to be able to tell me that. So when you have your test, you're going to have a separate one that you got to understand and know this. So probably be a few of them in the multiple choice, but it's also going to be some on your separate part that you have to do this. Now, this is what I was saying about everything getting pulled together. Now, free energy in equilibrium. Under any conditions, standard or non-standard, it doesn't matter. The Gibbs free energy can be found this way. Delta G is equal to delta G prime plus RT natural log of Q. Oh my goodness. We still seeing universal gas constant. We seeing Q. Q is the same as K, as you've seen before. And under standard conditions, concentrations have to be 1 molar. So Q is equal to 1 and natural log of Q is 0. That last term drops out. So what does that mean? Equilibrium, we talked about this. Q equals to K. Delta G equals to 0. This is how the equation looks. So 0 is equal to delta G prime plus RT log of K. If you rearrange it, you get this, or you get another K, you guys. K is equal to E to the negative delta G over RT. So when I said that there was going to be a lot of this, and this is where I'm saying is everything that you've had so far is coming together in this picture. So you're going to see all of it coming together in this aspect. When we get to the next chapter and we go into the next 2 chapters, you're going to see everything else relates, because the Gibbs free energy is going to relate to electrochemistry, which is going to relate to nuclear chemistry. So all of this is just coming together. So what is my advice? Make you a formula sheet. Go ahead and start making a formula sheet and start learning those formulas. Make sure you have them in your head. Learn those formulas. Those are very important. So make a formula sheet. I may even give you some extra points on making your formula sheets and uploading them, because you're going to need those. So that will help you. Make sure you have your periodic table. You need to have that when you're taking these next tests, because the molar masses and all of that stuff. Appendix C, you're going to need that. So these formulas you need to know. Now, when you talk about reactions, they're not going to happen alone. And remember what I was just saying, that I just gave my students a test on this. This is what they tested on today in biochem. This is what we're talking about right here. Nature couples them often to favorable reactions. So they're talking about ATP, and ATP goes to ADP plus PI. And this happens when you are talking about glucose. Basically, what happens inside of your kidneys. when people are trying to produce insulin or trying to get rid of sugar when it comes into glucose form. And this is what it is. Glucose oxidizes, and this is what happens in the cell. You have oxidation, and then if you got high free energy, it goes to ATP, but if it's low energy, it's ADP. And then that goes in and out for cell development. So free energy releases ATP, and what happens with the ATP when you see it in biochem, those little legs of ATP, they like to walk. And so they have to move. So if they don't release it, they won't move, they'll just stay there. And so this is what's going on. So what I wanted you guys to know is that you will see this again. This is not anything new. You will see it. You will see it in organic chem. Um, and you will see it in the first part of organic chem. You will see it in organic. So I don't want you guys to forget this, because when I see you guys in the fall, you will see this in organic chem as well. So I want you guys to understand that and make sure that uh, this is all that I have for today. I'm not going to get into too much of all the chapters at once. I want you guys to go and digest this. Please go read the chapter, make a formula sheet. Let me do this. Let me hit a share. My Lord. And let me do this. Let me erase. All right. Now, there are some things that I want you to do. First off, read the chapters. Read the chapters. Go ahead and read all 3 chapters. Do your concept map. That's what I want you to do. So chapters 19 through 21, let me make sure I put it up here, because I'm going to put it on here. 19 through 21. Read them. Go back and reread that. Do your concept maps. Make a formula sheet. Okay, now I will say this, because I'm putting this in writing. I've taken away all of the Newtons. You do not see them there. They are gone. So you don't have to worry about that. However, you will have Pearson work. I'm not trying to be mean or anything like that. You guys paid for the Pearson. You guys are going to use the Pearson. That is going to help you study for your final exam. Because your final exam, yes, is going to be online, but the questions are going to be very similar to that of a standardized test. So the Pearson will help you. Now, as far as the homework and all of that, it's just going to be a few problems. So we're going to go over that. You will have some Pearson. It's not going to be much. It's just something that to help you study. So this is basically going to be study for final exam. And that's going to be basically your problems from chapters. And that's from, I think it's going to be from all the book. I have to check and see. Study for final exam. And what it is, let me take a look. So this last part, molar solubility, entropy, standard conditions, all of that would be on there. Let me see. I'm trying to see what else would be on there. So what we just covered would definitely be on your final exam. And let me see. I'm gonna pull up something to make sure. But uh, yes, you're gonna have a lot of stuff that is on this test. So the stuff we just went over today, all of this will be on your final exam. I'm just trying to make sure stuff from last chapter and the last test will be on that exam. I'm trying to see if there's anything else. We'll have Pearson work, study for the final exam. And I will say review all your concept maps. Because the concepts that we're going over, if you don't have them on your concept maps, you need to redo your concept maps because that's going to be playing an integral part in you passing this exam. So make sure you do that. If you guys got any questions, send me an email and let me know, but I will be doing a few Pearsons. It's not going to be much, but it'll give you some indication of what's going to be on the exam. That's why I want to give you that so that you guys can have some practice. Like I said, because y'all paid for, Newton was free this semester, but because y'all paid for the Pearson, you guys will use that. And the Pearson, both of them will line up the same. The Pearson will be a little tougher, but being a little tougher will ensure that you will do better on the exam and you'll know what to expect. That's all I have for today. If you got any questions, make sure you send me an email. I'll have my phone nearby me because I got to go tackle whatever my kids did behind me real quick and everything. So questions, let me know. Like I said, I miss you guys. And I will talk to you guys on Thursday. Have a good one.